taking a look at the strength of acids and bases. Our goal is to describe and differentiate between strong and weak acids based on qualitative analysis. And this is actually outcome 4, not 14. Acids and bases can be distinguished from another by diagnostic tests such as litmus or pH tests. Acids with the same initial concentration can have different variations of acidic properties. If we are going to study these properties, it's very important to control variables such as concentration and temperature to obtain comparable results. So if we have a beaker of what we're going to look at is a strong acid and a weak acid, if we want to compare their properties such as pH, conductivity, etc., they need to have the same concentration and they both need to be at the same temperature conditions. So an acid or base is described as a weak acid or base if its properties under the same conditions, so temperature and concentration, are less than those of the strong acid or base. So comparing here, strong acids have a high conductivity, weak acids have a lower conductivity. This is because there are fewer of them ionized. Strong acids have a high rate of reaction with active metals, meaning that they will bubble very furiously, whereas weak acids have a slower rate of reaction, so they'll just bubble a little bit slower. Strong acids have a relatively low pH. Weak acids have a mid-range pH. So if we're looking at the acid-base scale, 7 down to 0, remember it can go lower than 0. Typically, if they have the same concentration, we'll see probably about like 3 or 4 to 7 is where we'll find our weak acids. Our strong acids will be in a pH less than that, so much closer to 0. Strong acids have a high concentration of hydronium or H3O plus ions in solution. Weak acids have a lower concentration of those ions in solution, again, because they do not ionize completely. Strong acids react completely with water to form H3O plus, whereas weak acids will react very little with water to produce H3O plus. There's only 6 strong acids. Every other acid is considered a weak acid. So a very blurry picture here, but just kind of looking at it again. A strong acid, if the acid is a proton, aka a hydrogen ion, and a negative ion, aka an anion, like Cl minus, an acid molecule would be an H and that Cl, or whatever this negative was. When we put a strong acid into water, initially all of the molecules are together as an acid molecule. And when we place them in water, they ionize completely, aka they break up completely. That means that there's that high concentration of H3O plus in water. Weak acids, on the other hand, they're added to water again as a combined molecule. When they hit water, less than 50%, usually closer to 1%, of these molecules actually break apart. So when we look at water, the weak acid, in water, most of these molecules are still stuck together, and only a select few have actually ionized and broken apart into water. So if we added the same number of acid molecules for both a strong acid and weak acid, the weak acid will have a lower concentration of H3O plus because most of them are still stuck together. Strong base and weak bases act very similarly. Strong bases have a high conductivity, they have a high pH, they are considered soluble ionic hydroxides, meaning it's a metal with OHs. Now, this has to be soluble, meaning that it has to dissociate in water. Okay, if it does not dissociate, it's considered weak. A strong base dissociates completely in water, and we have this equation here where MOHX, solid, so the ionic hydroxide, dissolves in water to be MX plus. Remember, X would be its charge, so if it was a charge of 3, we would need 3 OHs. That's why that little X is there. So MX plus and then X number of OHs. Weak bases have a relatively high conductivity as well. okay, with the exception of ammonia. And this is because most of them are ionic compounds still. It's just that their anion was the one that went to react with water. So because they're all ionic, they all still have a high conductivity. Ammonia, on the other hand, is NH3, and it's molecular. So that's why it has a bit of a lower conductivity. The lower pH means it's closer to 7. It does not mean it's less than 7. Our strong bases would be up around like 12 and 13, and our weak bases will be less than that or greater than 7. Weak bases have to react with water, and they react incompletely, okay? Reactions are not 100% when it reacts with water. So anything that has to react with water, like for instance, carbonate, makes HCO3 minus and OH minus. This reaction is not 100%, like our strong acids. Again, it would probably be less than 50%. The general form of this reaction is some sort of base molecule with water, creates OH minus, and then the balancing entity, aka like HB plus, or whatever we've decided B was, where the H from water has moved to B. That's what this is. All right, so that was it for strong and weak bases and acids. We're going to look at monoprotic and polyprotic acids and bases. So acids that have only one acidic hydrogen in their compound formula and react only once with water to produce H3O are considered monoprotic. So for example, HCl is monoprotic. It has only one H here. And when it reacts with water, it makes one H3O plus and a Cl minus. And this Cl minus is unable to go and react again. So acids that are monoprotic have only one H, will produce only one H3O plus, and their anion here cannot react again to give up another H. Polyprotic acids, on the other hand, have multiple acidic hydrogens in their compound formula and can react more than once with water. So for example, H3PO4. H3PO4 has 3 acidic hydrogens, so we can anticipate that it's probably going to react 3 times. So we show it reacting with water, and we'll make one H3O plus, and we'll be left with H2PO4 minus. Now this H2PO4 minus can react again because it still has acidic hydrogens. So another reaction with water, we make an H3O plus, and we're left with HPO4 2 minus. Now, this still has an acidic hydrogen, so it can react one more time. And I know it can only react one more time because there's only one more hydrogen to give up. So we are done at this point. It cannot react again. Okay, note that in general, polyprotic acids are weak acids whose reaction with water decreases with each successive step. What they're saying is H3PO4 is a weak acid to begin with, meaning that it reacts with water less than 50%. So this reaction, maybe 50% of it will actually happen. So let's say we started with 100, oh no, that's 1,000. 100 of these. We will produce less than 50% of these will react. So let's just say 50% react for ease here. I'm going to get 50 H3Os and 50 H2PO4s. So those 50 H2PO4s can go and react again. Now, this reaction happens less. So it's less acidic, meaning its reaction happens less. So let's say it's 10% of them that react this time. So out of my 50, only 5 will react to make 5 H3Os and 5 HPO4, 2 minuses. Now we have all 5 of those to react. And let's say this reaction, again, happens less because it's less acidic each time. Every time it loses an H, it becomes less acidic. Let's say this happens 1%. So 0.05 of these would be produced. Now, a lot of people, when they see that we have H3PO4, we say, well, it can react with 3 waters. And we make 3 H3Os, and we're going to be left with a PO4, 3 minus. All 3 of these are added to waters. What this implies is that each reaction with water is identical, and we know that it's not. So we need to make sure that when we have something that's a polyprotic acid, we show every reaction with water. It's a weaker acid every time it loses an H, and we cannot actually say that it reacts 3 times like this. This is a bad reaction because, again, it does not react equally with each water. Additionally, this implies that this reaction would be complete. So meaning that we made, from all 100 of those, we made, 300 of those H3Os. Now, if you added those up from our initial, we had 50 and 5 and 0.05. So we would have had 55.05, which is much less than this 300. Again, this implies that it's a strong acid, reacts completely, and we know that it doesn't. Therefore, the pH of H3PO4 won't be any lower, I guess, because it's an acid, than HCl with the same concentration, even though it has 3 hydrogens to give. Note that H2SO4 is a strong acid. So its first reaction with water makes an H3O plus and HSO4 minus. This reaction happens 100% because this is a strong acid to begin with. However, when HSO4 reacts, HSO4 is not a strong acid. So when this reacts to make H3O plus and SO4 2 minus, it's a weak acid now, so it'll happen less than 50%. So H2SO4 is a little bit funky as a polyprotic acid because its first reaction is 100%, but then it makes this weak acid that reacts less than 50%. Monoprotic bases are bases that can only react with water once to produce hydroxide ions. Note that compounds like barium hydroxide are actually monoprotic even though there are 2 moles of OH produced. So barium hydroxide has 2 OHs. When it's put in water, our first step is to dissociate, and with that we see it makes hydroxide. Because it makes hydroxide in one step and it cannot react again, we consider it monoprotic, even if it makes multiple OHs in that one step. Another example of a monoprotic base could be something like NaNO2. So our first step is to dissociate, and this is not part of our acidic basic reaction, so this is not considered a step. So NO2 minus. NO2 is not one of our neutral ions, so it can go and react with water. And it'll make HNO2 and an OH minus. Because it's neutral, we're going to stop adding to it. It will not react again. Again, this step does not count as part of our reaction count for polyprotic because the first step is just to dissociate. We only had one acid-base reaction here, so it is considered monoprotic, or it can only accept one H. Polyprotic bases are bases that can react more than once with water. So for instance, carbonate can react with water once here, And remember, this is a weak base. It's going to steal an H from water to make HCO3 minus and leaving an OH minus from water. This HCO3 can go and react again with water to make H2CO3 and OH minus. So it cannot react again. It's neutral. It won't accept another H. Know that again, it gets weaker after each reaction. And one other thing to note is sometimes people are like, well, HCO3 from this step reacting with water could make H3O plus and CO3 2 minus. That literally just went backwards here. So once we start making a base, we are going to continue making a base with polyprotic substances. So do not mix acid and base reactions for these. Note in general that polyprotic bases are weak bases whose reaction with water decreases with each successive step. So same idea here. CO3 2 minus is a weak base, so it reacts less than 50% the first time, and it'll react even less than that the next time. So let's say 10%. So if I had 100 of these, I only make 50 of the products. Only 50% of these will react. Therefore, all 50 of those can go and react, and they will only react 10%. So let's say we make about 5 of each of these. So again, it is incorrect to write a reaction where CO3 2 minus reacts with 2 water molecules to make 2 OHs and H2CO3. Incorrect. Because again, it implies that each reaction with water is identical, and we know from our work here that it is not.